Hello, this is Mr. White, and this video is on series, also known as sums of sequences. By now you should be pretty comfortable with all the vocabulary terms and concepts over here under sequences. You should be comfortable writing explicit and recursive rules for sequences, knowing the difference in dealing with arithmetic and geometric sequences, and we should also recognize that there are some sequences that are neither arithmetic nor geometric. In fact, one could argue that most of them are neither, although we've tended to deal with just these two. But if any of those concepts here are not clear, please run to office hours and get it cleared up, because you really need to be solid on all that before we proceed. All right, so we're delving into series, and at least as of the recording of this video, this year we just delved into sigma notation. And I've even shown in class, I've hinted at the contents of this video. I've probably shown how we're going to come up with a formula for calculating the sum of sequences, specifically arithmetic sequences. So all the things I have boxed in right here, right now, are the contents of this video. We're going to delve further into that. Now I should point out that our book and some other books and some resources tend to have a nuanced distinction between what they call a series versus a sum of a sequence. I'm going to ask that you think of them interchangeably. So when I say series or when I say sum of a sequence, I'm saying the same thing. All right, once again, we're going to say geometric. We're going to say that one for the classroom. All right, so I'm going to summarize what I've hopefully already shown you in class already. Every year I always see some students seem to get this right away, but there's enough students whose eyes kind of glaze over that I think it's worth showing again here and just letting it soak in, seeing it a second time. I'm about to show you the approach that we're going to use for summing up an arithmetic sequence, aka getting an arithmetic series. So let me stress that what we're doing here on this slide is only applies to arithmetic series. And I'll ask you to ponder why the process that we go through wouldn't even work for anything other than arithmetic series. All right, so the idea was that this diagram represents a series of n rows. So however many rows I have in this picture, just consider that could be any number of rows n. And we're going to let this distance right here, that represents the value of the first term in the series. So if that first term were 10, then I'd ask that you assume that that is 10 dots. If that first term in the series were 100, then I'd ask that you just imagine that this is 100 dots. And this represents whatever the last term in the series is, the nth term. So again, a sub 1 is the first term, and a sub n is the last term. And there are n total. All right, so visually, this makes a compelling argument for the formula that we're about to come up with. If I take this and duplicate it and rotate it and move it over, I will notice that, once again, I have a sub n dots over here. And if I want to know how many dots are in this total rectangular grid, I'm going to take this length of this rectangular grid, which is a sub 1 plus a sub n, right? And I'm going to multiply it by the width of the rectangle, which is just n. Now, I don't really want all the dots. I want only half of them. So you're going to notice that sometimes you may choose to put the 2 underneath the whole thing. You may choose to put the 2 just underneath the n. I tend to like to put it underneath this. Ultimately, it doesn't really matter between those various options, but I tend to like that last one. I'm going to show you why. I'm going to ask that you envision, or consider this to be just the average of the first and last terms. I mean, that's exactly what it is. Remember, first term, last term, and when you add two numbers and divide by 2, this is just the average of that first term and last term. And for arithmetic series only, it is also the average of all the terms. And I ask that you look at the diagram and convince yourself that not only is that the average of the first term and the last term, but it is the average of all those terms. Okay, and therefore, just by the definition of what an average is, if you multiply it by the total number of terms, you should get the total sum. This is one of those things that I'm going to claim. It needs to make sense to you, and if it doesn't, please pursue getting to that point where it makes sense. So if I write this in series or summation notation, I would put I equals 1 all the way up to n. Now, normally we'll put the actual explicit rule right here, but I'm trying to keep this very general. So that would be the rule for whatever arithmetic series we're dealing with. Okay, so here it is presented in the book. And again, like I said, the book tends, rather than just call it a series, as I would, it says this finite arithmetic sequence, whatever, consider it the same thing. Here's the formula that I just demonstrated. And I also want to make one more point here before I do an example. There's one more formula underneath the block, which I'll reveal in a moment, but it's one of those formulas where, again, I'm not going to use it a whole lot, and if you use it, I at least want you to see where it came from. I'm going to steal from one of the previous lessons, where rather than go through it in depth here, I'm just going to throw this on the screen and hope that you recall how we determined that the nth term in an arithmetic sequence would be the first term plus that common difference multiplied by n minus 1. And again, I really need you to understand why that makes sense rather than just memorize that formula. But if you take this formula and substitute it in for this a sub n here, you would get n times a sub 1 plus, now again, here's where I'm going to substitute. Instead of a sub n, I'll write this formula over here, a sub 1 plus b times n minus 1. And let's see, it's all over 2. The book chose to put the over 2 here, just like I did. And then when I reveal this block, and you look at the alternate form of the formula, it really shouldn't be that mysterious. A sub 1 plus a sub 1 gave us this. D times n minus 1, and now it's in a different order, but same thing. N over 2. So it's just a rewriting of the earlier formula. And again, I'm going to tend not to use that one. I feel like this first one here is just more intuitive. But if you use that alternate form, you're going to be responsible for knowing it and memorizing it and making sure it makes sense. All right, let's get to an example. So let's say we're looking some years down the line. Let's say you earned $40,000 in your first year working right out of college. And each year after that, you earned a $600 raise. So this year, you earned a fat $50,800 salary. And our first task is to write in sigma notation, or summation notation, the series representing the total money that you've earned over the years. And we're going to ignore such ugly practicalities as your gambling debts, your bail money, child support, whatever. And our second task is going to be to calculate the sum. All right, so again, I'm going to speed through the parts that you should be comfortable with by now. I hope you'll pause, let it sink in if need be, and seek help where necessary. But for part A, sigma notation, notice I didn't tell you how many years you've been out of college. So we're going to need to figure that out. We're going to rely on this fact that the nth term in an arithmetic sequence or series, or I mean sequence. The nth term in an arithmetic sequence is the first term plus the common difference times n minus 1, right? Again, it's from a previous lesson. In this case, the a sub n is that 50,800. That's the last term that we want to add. So 50,800 equals a sub 1, that's the first term. So the first and last terms were given to us, and that will help us figure out how many years you've been out of college. The d in this case, the common difference, every year you're adding 600 on top of the previous salary, so 600 times n minus 1. All right, so let's subtract 40,000 from both sides. That'll give us 10,800 equals 600 times n minus 1. It seems to me that most of my students tend to want to distribute that 600. I'm not really in favor of that. I'm going to divide both sides by 600. Now, I'm not saying you're going to get the wrong answer. I just tend to think this is the what I'm doing is the cool kid way of doing it. So how many times does 6 go into 1,800? That's going to be 18. So 18 equals n minus 1, and therefore 19 equals n. And again, I need you to recognize that this is the number of years that you've been out of college in this scenario. Man, you're getting old. All right, so let's write this in summation notation now. Let me get the graphic out of the way. I don't need all that money distracting you there. All right, so for part A, sigma notation, summation notation. We have enough information now. We'll put the sigma here. We'll put n equals 1. Actually, let me use I for this one. You're not confused things. I equals 1. And up top, I said n was the number of years. That's why I didn't want to use n down below. But I'm going to put 19 here because I know what this n value is. And again, instead of putting a sub I like I did on the previous slide, we actually have enough information for an explicit rule. So I'm going to put that instead. I've said in the past that I don't mind if you just leave that unsimplified. There are actually some advantages to leaving it unsimplified, one could argue. So I'm cool with it. And that is part A. Sigma notation or summation notation representing the sum. Now again, we haven't calculated sum yet, that's part B. So let's get on to that. Part B, pretty straightforward. That's where I'm going to use that formula from the previous page. And again, I hope you don't feel like you're memorizing this. I hope this just makes sense that I'm going to take the average of all the salaries for all those years. And again, for arithmetic sequences, the average of all the salaries for all the years is the same as the average of the first and last year's salary. So if I just take the average of the 40,000 and the 50,800, I take the average of those two numbers, that's the average number for all the years, multiplied by the number of years, which we determined is 19, and that is going to give me the total sum. So I'm going to trust you can do that on your calculator with ease and get the same result that I do, which is 862,000. I'm trying to shortchange it here, apparently. $862,600. That is how much you've earned over your 19 years out of college. Congratulations. All right, let's do one more that just has a subtle difference. Some things in common, but a subtle difference. I was actually at a friend's house this weekend, and I got a little distracted when he was talking. We were in his backyard, and I was counting the bricks that were in this sort of circle pattern, similar to the one you see up here on the board. And reminded me, it kind of inspired this example. Let's say you're designing a brick pattern for your back patio, similar to what you see here. The innermost row contains 10 bricks. So on this picture, 10 bricks right there. And each successive row contains 3 more than the one before it. Let's say you plan for 12 rows in all. I didn't draw all 12 in this diagram here, but pretend that there's 12 rows there. And how many total bricks will your pattern use? So I'd like to keep the graphic on here, but let me shrink it down at least. So write in sigma notation, the series representing the total number of bricks. That's going to be easy enough. I'm going to do that fairly quickly again. Sigma, this time, unlike the last example, you're told how many terms there are. There are 12 rows. So we'll go from 1 to 12. And once again, we'll find that we'll use our previous lesson skills to say that the explicit rule is 10 plus that common difference of 3. That's being added to each row as I go outward. So in this one, I didn't have to do any work to figure out this number. It was given to me. All right, so for part B, where we actually calculate the sum, this is where I'm going to have to, the last example, you're given the last term in the series. This time I have to figure it out. I'm going to use my explicit rule to do that. A sub n, which actually I know what n is. The last term is a sub 12, equals 10 plus 3 times 12 minus 1. And that's going to give me, let's see, 43. Now, why do I need to know this? Well, because I need to know it for my formula, right? That the total number of bricks is going to be n times a sub 1 plus a sub 12 this time over 2. And the n in this case, we said 12 rows deep, so let's erase that and put 12. The a sub 1 and the a sub n in this case I know now. A sub 1 and a sub 12, or a sub n, is 10 and 43 respectively. And once again, pretty easy to calculate, but that would be 318 bricks. All right, I hope that I didn't go too fast. Some of the parts I trusted that you knew from previous lessons. Hope that made sense. Let's have you give it a try. Here's an actual picture that I found on the internet of some cans stacked into a pyramid. And like me, you're probably wondering how many cans that is. So you're going to figure it out. If you're viewing this on the device where it's a little hard to read that text, let me enlarge the text for you here. All right, have at it. Okay, let's see how you did. There are my solutions. I'll point out that as part of the first problem, you needed to figure out that there are 195 cans in the bottom layer of that stack. And in the second problem, you needed to figure out that there were 33 rows.